A lot of machine learning is about minimizing loss functions, and the way you do that depends in part upon whether the function is convex. Today we'll see how we can check that. So we'll review the second derivative test for convexity, and then we'll go through a whole slew of examples. We've already seen what it means for a function to be convex when we have a function of d variables. It's convex if its second derivative matrix, which is a d by d matrix, is positive semi-definite at all points. Okay, so what exactly does this mean? So at any given point, the second derivative matrix is a d by d matrix. It's positive semi-definite. A matrix H is positive semi-definite if the quadratic function defined by the matrix, x transpose hx, is always greater than or equal to 0, no matter what x you plug in. We also saw an alternative characterization of positive semi-definite matrices that is somewhat easier to use in many situations. Okay, so a matrix is positive semi-definite if it can be written in the form U transpose, where U is any old matrix. Okay, so we'll be making use of both of these definitions. So let's look at an example. This function, f of x equals the length of x squared. Is it convex? Well, the first step is to compute its second derivative matrix, the Hessian. And we actually did that last time, and this turned out to be twice the identity matrix. Is that positive semi-definite? Well, let's see. What is Z transpose times twice the identity times Z? Well, we can pull the two out, and we get Z transpose times the identity times Z. The identity times Z is just Z. So this is twice Z transpose Z, which is twice the length of Z squared, which is greater than or equal to 0. So this is positive semi-definite. Another way to see it is that that matrix, twice the identity, is a diagonal matrix, and all the entries along the diagonal are positive. So the matrix is positive semi-definite. Good, so f is a convex function. It looks like a bowl. And in fact, it's the high-dimensional analog of our classical convex function y equals x squared. Okay, this is the d-dimensional version of exactly the same thing. Let's do another example. Okay, so here u is any fixed vector in d-dimensional space, and we define a function, f of z. So z has d variables, z1 to zd. And f is simply the dot product with u squared. So it's u1 z1 plus u2 z2 all the way to ud zd squared. Is this a convex function? Well, let's start by computing the second derivative. Okay, so first, what is df dz? What is the first derivative with respect to z sub j? When we have something of the form something squared, we first pull down the 2, then we copy down the whole expression. And then we take the derivative of the inside part with respect to zj, and that's just uj. Okay, so that's the first derivative with respect to zj. And now let's take the second derivative with respect to z sub k of this thing. Okay, so we're going to start with this, and now we're going to take the derivative with respect to z sub k. Now, in this whole expression, there's only one term that involves z sub k. Okay, and that's the term with uk zk. So the second derivative is just 2 uj uk. So the second derivative matrix is a d by d matrix whose jk entry is twice uj uk. One concise way of writing this is to say that the Hessian at point C is twice UU transpose. So do you remember this? If you have a vector, U, then UU transpose is a D by D matrix whose ij entry is Ui Uj. So that's exactly what we need in this case. Is this positive semi-definite? Well, UU transpose is positive semi-definite. It has that special form that immediately identifies it as being of this type. And when we multiply it by 2, it remains positive semi-definite. Okay, so this is PSD. And so this function is indeed convex. Okay, those were warm-ups. Let's move on to a somewhat more challenging example. So this, if you will recall, was our loss function for least squares regression. So we have a set of data points, n data points, xi, xj, where the x's are vectors in d-dimensional space, and the y's are the response values, real values. And we want to find a linear function given by w that minimizes the squared error. Now, normally we would also have an intercept term in here, a plus b. But if you recall, we had a way of assimilating that into w. So you can imagine that we've already done that, and that this is the function we now want to minimize. Is this a convex function? Well, let's start by computing the second derivative, and en route to that, the first derivative. Okay, so our function over here is the sum over I of yi minus w dot xi, that is w1 xi1 all the way to wd xid squared. Okay, so the derivative with respect to w sub j. Well, the derivative of a sum is the sum of the derivatives, so we can just pull the summation out. Then we have something of the form u squared. The derivative of that is 2u du, so we bring down the 2. And we have yi minus this whole thing over here, w1 xi1 all the way to wd xid. Okay. And now we take a derivative of just that inside part with respect to wj. So we get negative xij. Okay, that's the first derivative. Let's pull the minus 2 in front just for convenience. Okay, so we get something like this. WD XID XIJ. Okay, now let's take the derivative with respect to W sub k. So we take this expression and we take the derivative of that with respect to W sub k. So that's the second derivative. And what do we get? Well, for the term in the middle, there's only one term that involves W sub k. So we get negative x I k x I j. Okay? And so the negatives cancel out, and if we just copy this over, what we have is that d squared L with respect to wk, wj is twice the summation over I. Let's see what we had, xij and xik. So the jth coordinate of the ith data point and the kth coordinate of the ith data point. Okay, so this is the second derivative, or at least one term of the second derivative matrix. What's the entire matrix? Well, this is again something of that special form, UU transpose. If you remember, if you have a vector U, UU transpose is a D by D matrix whose ij entry is Ui Uj. Okay, so this entire matrix over here, the Hessian at W, is twice times the sum over I equals 1 to n of the ith data point transpose. Okay, this is a D by D matrix over here. So that's the Hessian. Is this positive semi-definite? Well, this particular term here does have that UU transpose form. So this is positive semi-definite. Okay. And we've already seen that if you have the sum of positive semi-definite matrices, that's also positive semi-definite. So this is also positive semi-definite. And we've seen that multiplying a positive semi-definite matrix by a positive constant again leaves you with something positive semi-definite. So the whole thing is positive semi-definite, and that means that this is a convex function. Okay? And this is one of the many reasons why we like the least squares loss function so much. Okay, well, that's it for today. I think we have convexity under control now, and in fact we have all the tools we need to get started on our next set of classification methods. See you soon.